Morning, everybody.
We're celebrating the end of last course.
Okay, so the first order of business, a reminder, we're going to have our exam on Wednesday, a week from today. Okay, so what is the exam going to cover? We're going to cover the first order and second order response. The different responses of the second order system: over-damped, critically damped, under-damped. You should be able to know the performance or the response of the system based on the location of the poles and be able to get zeta and omega n from the poles location. The second topic is going to be the stability and using Routh-Hurwitz to determine stability. What happens if the first column is 0? If we have a row of 0, and how to populate the table and be able to tell the number of poles in the right half plane. And also, we're going to have a problem on the steady state error. Now for the problem on the steady state error, I'm going to expect that you guys are going to be using the formulas that we developed for different inputs, for a step, for a ramp, for a parabolic input, and different system type, 0, 1, 2, etc. Any questions? Now the other topic that we could have also on the exam is the root locus. Do you want the root locus on the exam?
No, thank you.
Are you sure?
Yes.
Okay, we'll leave the root locus for the final.
No. I'm so sad we have a final.
Don't keep reminding me of that.
It makes me so sad that another class does it. We do.
Okay. Now you are allowed a 2/3 of a letter size formula sheet.
So this is the second, third.
The second
That's what we
third,
already did.
yeah.
Okay.
And they'll have another third for the final. Sounds good, everybody? Okay.
Are the solutions for the homework going to be posted for?
Yeah, I will post them. If I don't, I mean, just send me a note.
Also, do you know what homework we're supposed to know through? Like, homework, we should be able to do homework 4, 5, and 6, or just 4, just 4, 5?
I mean, you should be, I mean, if we cover the material, you should be able to do the homework. I mean, usually, I think the last homework we have is on root locus. You should be able to do it. You should be able to do all the homeworks. Hopefully, everybody is doing the homework. We're not doing the homeworks? Anybody not doing the homework? Everybody here is doing the homework. Looks like a Fort Walton problem. Or maybe they're shy, they're not answering. Should we go back to doing quizzes? I mean, if you do not like a final, you're going to like quizzes?
I would be okay with quizzes after, like the quizzes you did.
Okay, you know what we're going to do? After the second exam, we're going to going back to doing quizzes. Looks
The
like you're not
homework
doing the
quizzes?
homework.
So the homework quizzes and then instead of the final?
Oh,
Is that what you were saying? Because
No.
I will vote for that.
we're not negotiating here.
Look, they're voting too.
Okay. So what we're going to be doing today is we're going to finish the root locus, plotting the root locus, and we're going to start the second topic, which is the controller design using root locus. So we're going to do two examples in addition to the plots that we already done. And then we'll move to the next topic. And what I'm going to suggest we do is I'm going to give you probably 5 minutes to plot these root locus, and then we'll do them together. How's that sound? So if we are given g of s, that is equal to 1 over s multiplied by s squared plus 5s plus 6, and h of s is equal to a 1, we're going to plot the root locus. And if you factor this polynomial, it is s plus 2 multiplied by s plus 3. And I try to plot it, and then we'll do it together. You can look at the notes if you need help. Okay, let's do this together. Hopefully one of two things happened. Either you made progress and everything is straightforward, or you just realized, oh, I have to review this. I'm not sure how to use it. Because this is one of the things that when you see somebody doing it, it's really very simple math. But when you try to do it, you're going to, get confused unless you practice. So please make sure you don't look at the examples and think, oh, I know how to do it, I know how to do it. Look at the example, try to do it yourself, then compare the results to what we got. Okay, so the first step, given that we have g of s and h of s, we calculated the closed loop transfer function. We're going to look at the g of s multiplied by h of s. We have open loop poles that are at 0, -2, and -3, and we have no zeros. So therefore, we're going to go to the S-plane, and we're going to label our poles that are at 0, at 2, and at -3. And we can label also on the real axis which part of the real axis is going to be on the root locus. Which part is going to be on the root locus? This part and this part. Now, probably everybody realized, like, we got two things here. This is an asymptote as well. We got it also from the fact that the real axis is to the left of an odd number. Make sense? Okay. How many branches are we going to have in the root locus? We're going to have 3. We have 3 poles. We're going to have 3. These branches are going to start at the poles and they're going to end at zeros. We don't have any zeros. Therefore, the 3 of them are going to end as asymptotes. So therefore, the number of asymptotes, which is the number of finite poles minus the finite zeros, is equal to F3. And these asymptotes are going to meet at -5/3, which is going to be a point somewhere here. So at this point, all these asymptotes are going to be meeting, and they're going to be making an angle that is 60 degrees, -60 degrees, and 180 degrees. Okay. Now, apparently, we know how the root locus now is going to look like. This, starting at this pole, starting at this pole, these two branches are going to split, and they're going to go to these asymptotes. We can find this point here, which is the breakaway point. So to calculate the breakaway point, we're going to take k multiplied by g of s, h of s equal to -1. This is the equation that governs all the locations on the root locus. And therefore, k is equal to -1 over g of s, h of s, which in this case, because we don't have zeros, there is no denominator. When we flip these, it just becomes just a polynomial. We can, if you like, set s equal to a sigma. Why do we set s equal to a sigma?
To eliminate the...
Because the region we are interested, the values, the range of s that we are interested in is only the range that is on the real axis. Make sense? So we are only interested in solving this when s does not have imaginary parts. So we can replace s with sigma. And then we're going to differentiate that You're going to take the derivative of k with respect to sigma, set it to a 0, and that is going to give me negative 2.5 and negative 0.78. Now I'm going to come back to the root locus. If you remember, this was negative 2 and negative 3. But now I'm getting 2 points. One is negative 2.5, negative 0.78. What are we going to do with the negative 2.5? We're going to ignore it. Why are we going to ignore it? Because it does not belong to the root locus. This region does not belong to the root locus. So we're going to take only the sigmas that belong to the root locus when we do the breakaway point. So this one, ignore. It does not belong and therefore our breakaway point is negative 0.78. So we can come here and negative 0.78, and our branch is going to split from here and is going to go like this. It's going to split here and is going to go like this. Together? So these are our asymptotes. It's going to split in here. Now we can also, go ahead.
So when you say that sigma is not part of the root locus, do you mean it's not within the bounds of the two poles?
No, because on the real axis we determined the only valid values of sigma is when it is between 0 and negative 2, negative 3, and to infinity.
Okay, and the negative 2.5 is...
Negative 2.5 falls here.
Okay.
It's not part of the root locus. Does that make sense?
Thank you.
So always when you calculate the breakaway breaking point, you have to make sure they're part of the root locus. If you get values that are not, you just ignore them. Okay. So then what we can also do, we can use Rutherford to find where this intersection with the j omega axis is. And therefore, to do that, we're going to calculate the closed loop transfer function. And we're going to get the characteristic equation. We're going to do the route table. How do we find the j omega axis? We want a row of 0. So I'm going to set this value of k here to give me a row of 0. Together? So if we have k equal to 30, I'm going to end up with a row of 0. If there is a row of 0, what does that mean? It means I have an auxiliary equation on the row above it. And therefore, when k is equal to 30, 5s squared plus k is the auxiliary equation. And therefore, I can solve for the value, or solve this equation to find the value of s, which is going to be 2.45 plus j 2.45 plus or minus. Is that clear, everybody? So therefore, we can come here and label this point as j 2.45. And this is negative j 2.45, and this is when k is equal to 30. Any questions?
Can you go back to that second page for a minute, please?
Mm-hmm.
Thank you.
Is that clear? Everybody? Okay, I'm going to go back to the first page. And I'm going to ask you, for what value of k is the system stable? I mean, probably people who've done the lab yesterday should answer right away. K is less than 30. Excellent. How do I know it's k less than 30? Because when k is greater than 30, I'm going to be going this way. I'm going to be going to the right side. how did I know it's k less than 30 is stable versus k greater than 30 is stable?
As this k gets bigger, it's gonna go towards.
Yes, because when k is small, we're starting at the poles, and I know I'm gonna be having my roots here, and then as I increase k, it's gonna start going, and then crossing the j omega axis. Okay. Now, of course, you can see here, when k is very small, I'm gonna have my poles somewhere here, somewhere here, somewhere here. What is that response gonna look like? Stable. What is it gonna look like? Which one? It's gonna be overdamped. On the real axis, it's going to be overdamped. Together? What happens when I increase the gain? They're going to move closer, closer. Eventually, I'm going to have two poles on top of each other here. I don't know if you can see where I mean by here. They're going to be on top of each other. I'm going to have another pole here. What is it going to be? Critically damped. And then I'm going to increase k further. What's going to happen? I'm going to move, the poles are going to move somewhere here, somewhere here, somewhere here. What is the response going to be? Underdamped. Together? Everybody? What is the response of this system? What is the order of the response of this system? Second or third order? Third order. It is third order.
Because of that.
But why did we approximate it with the second order? Why did we say underdamped and critically damped, even though these are characteristics of a second order system? Because we're assuming the third pole is much farther than these, that we can approximate it with a second order system. Make sense? Everybody? Yes? Okay. Okay, let's do another, or the last example we're going to do. We have a system that is given by h of s, g of s, h of s, that is equal to s plus 3 divided by s squared minus s minus 2. And therefore t of s is equal to k multiplied by s plus 3 over s squared minus s minus 2 plus k multiplied by s plus 3. And I try to plot it, and then we'll do it together. Okay, can I do it together? Okay, so looking at this system, we have two open loop poles, and we have one open loop 0. So we're going to label our poles and zeros. 1, 2. We have a pole at 2. We have a pole at -1. And we have a 0 at -3. Which part of the real axis is on the root locus? It's going to be between the between 2 and -1, and -3 all the way to infinity. We have two branches, and we're going to have the number of we have two branches. One branch is going to end up at a 0, and there is one branch that's going to end up at the asymptote. Together? Now, since this is the asymptote, we know, like, we're already taking care of the asymptote, but nevertheless, we calculate sigma is gonna, the point where the asymptote is gonna meet is at 4. The angle of the asymptotes is only 180 degrees. We plot the asymptote, which is this one, the branch that we already plotted. What is the value of this sigma here? No value. This sigma, it has a value if we have more than one asymptote. If it is only one, they're not intercepting anywhere. Make sense? Okay, so we're going to calculate the j omega axis crossing. If you look at the characteristic equation of the closed loop transfer function, it is s squared plus k minus 1s plus 3k minus 2 equal to a 0. If I want the roots on the j omega axis, what should this term be? 0. I don't need to even do this. If I set k equal to a 1, this is going to disappear. I'm going to have s squared plus 1 equal to a 0, and that is going to give me where the j omega axis crossing. But nevertheless, to be consistent, we're going to do the right table, s squared 1 to k minus 2, k minus 1. If we set k equal to a 1, this row is going to disappear, which is the same as saying we're removing this term from this equation here. And therefore, the j omega crossing is going to be at j equal to, at s equal to plus minus j1. Together? Everybody? Okay, we're going to calculate the breakaway and break-in point. So we can go, let's go label J1, this point here is going to be a crossing of the j omega axis. And we're going to calculate the breakaway and break-in point. And to do that, we calculated the k multiplied by g of s, h of s. Then we write k equal to -1 over g of s, h of s. We replace s with sigma. We take the derivative, we set it to 0. And we're going to find that sigma is equal to -6.2 and 0.16. So these are our break-in, breakaway point. Okay, so we can come. How do you think this is going to look like? What is it? Can I have everybody point with their finger how it's going to look like? What is it?
Maybe a circle.
Then do like this. it is going to be, we're going to have a breakaway point at negative 0.16, which is going to be somewhere here, and it's going to come back at negative 6.2, which is somewhere here, and it's going to look like a circle, something like this. Make sense, everybody? Okay, what happens when k is very small? Is the system stable or unstable? Stable? Unstable. Why? Because we're gonna start with a pole that is in the right hand plane. K is very small, unstable, unstable, unstable. K equal to 1 becomes stable. K increases. We're gonna be going all the way here and then going this way. Make sense? So when k is equal to 1.5, what do you think the response of the system going to look like? Underdamped. Excellent. It's going to be underdamped, underdamped, underdamped. We keep increasing k. Eventually, it's going to go back to being overdamped. Is that clear? Everybody? Okay. So hopefully we've done enough examples on the root locus to cover most of the cases that we will see. And we've done 4 different root locus plots also in the lab. So between what we've covered and what you've seen in the lab, hopefully you have a good exposure for all the possible root locus you might see. Okay, now the next topic that we're going to be covering is we're going to be designing a controller using root locus. So we're not leaving the root locus. Now we're going to use the root locus to be able to design a controller. So as we've seen from the root locus, if one way to control the response of the system was to adjust the gain of the system. So as we've seen in this example, I have some control of how the system is going to behave based on the value of k. I can make it underdamped, overdamped, critically damped, etc. So adjusting the gain k gives me control over the location of the poles and therefore it gives me some flexibility in controlling the system response. However, some cases adjusting the gain alone is not going to be sufficient. And in this case, we need to change the dynamic of the system. Okay. So going back, looking at this example that we just had here, again, adjusting the gain give me some flexibility. I can move and get different responses. But what if I want my response such that the poles have to be located at this location and this location? I'm not going to be able to. Make sense? There's no value of the gain that is going to give me a system response such that the poles are located at these locations. But what if these are the specifications for my response? I want it such that based on zeta and omega n, I want the poles to be located at this location. What do I have to do? I have to shrink the root. I have to change the root locus. With the gain alone, I'm not going to be able to do that. Therefore, I have to change the dynamics of the system. What does that mean? I have to add poles and zeros so that I can change the shape of the root locus. And this is done through the controller. And what the controller is going to do is going to change the shape of the root locus. Okay. So let's look at two examples where we can justify what we're trying to do. So we're going to look at an example where the system transient response is okay, but the steady state error is not okay. Okay. So in this example, we are given this system. And for this system, we have a design specifications. We want the requirements. We want an overshoot that is less than 25%. And we want a small steady state error due to a ramp. And we want that error to be less than 1. Okay. So what do? We're going to come here. We're going to plot the root locus. And the root locus is going to look something like this. This is -5. This is -1. Okay. So we want an overshoot that is less than 25%. So from the overshoot, we can get the value of zeta that we need to operate at. And zeta is going to be greater than or equal to 0.45, the value of zeta. So from the overshoot, we calculate the value of zeta. Zeta has to be equal to 0.45. And we know cosine of theta, that made with the real axis, is equal to theta. So therefore, theta has to be less than 63.2 degrees. Do you remember all this from the second order system? What is the real coordinate here? Zeta omega n. This is omega n, and this is omega n multiplied by 1 minus zeta squared. This is theta. So again, from the overshoot, if I want overshoot to be less than 25%, then theta, the poles make with the real axis, has to be less than 63 degrees. So therefore, I can come here. I can plot a line here that makes a 63 degrees, 0.2 degrees. I can find the intersection point here. And this intersection point is going to be when k is equal to 4.188, and it's going to be at negative 0.404 plus or minus j 0.802. Does anybody know what I'm doing? No? Anybody does not? Don't be shy.
What is the green line?
Okay. Good question.
You're getting an intersection between the green line and the root line?
Yes, I want to know what the questions, and then I'll what other questions beside the green line? No, why did you choose the color red? Okay, so let's look at this. We plotted the root locus. The root locus looks something like this, the red one. That's the red line. Now the requirement is we want zeta to equal, we want overshoot to be less than 25%. That is exactly the same as saying I want theta to be less than 63.2 degrees. What is this theta?
The angle of the green line.
Remember, from the second order system, if I have a pole here and a pole here, and I connect this and I take this theta, cosine of this theta is equal to zeta. Make sense? Everybody? Everybody remembers that? Okay. So therefore, if I want zeta to be greater than 0.45, that's the same as saying I want the angle the poles make with the real axis to be less than 60 degrees, 63 degrees. Make sense? So what I've done, I said, okay, let me plot a line that makes a 63 degrees. If I intersect with this point, then this, what is the angle these points make? 63 degrees. Together? And that means if I'm operating at this point, zeta is going to equal to 0.45. Is that clear? Should I repeat it?
Did you make those numbers like for the k value up, or did you like find it?
For the time being, I use MATLAB. We'll do an example of how we found it. For the time being, I went to MATLAB. I plotted a line. I remember how you do a tip on the graph. I kept adjusting it till I found this point. It is k equal to 4.18, and this is the location. We'll see how to find it in a minute. Is that clear? Is that clear, Fort Walton?
We just use MATLAB for the test of this portion.
No, but you can use it after the exam. Okay. But the exam will be such that it is easier to do it by hand than with MATLAB. I'm sure you don't believe me, which is funny. Okay, so this is clear, everybody? This is fundamental because we're going to be using it throughout the design. So if anybody is confused, not clear where it's coming from, tell me. 3, 2, 1. Nobody said nothing? Okay. So again, this point represents all the poles that have zeta equal to 0.45. The intersection with the root locus will give me the location on the root locus that has zeta that is equal to 0.45. If I want zeta to be greater than 0.45, where am I going to be operating? To the right of the green line or to the left?
Say it again, sorry.
If I want zeta, remember, was it greater or less? If I want zeta to be less than 0.45, do I operate here or here? If I want it to be less than 0.55, I'm going to be operating in this region. This is going to be more underdamped. Remember, eventually it's going to be oscillating here. Together?
Lower the zeta.
If I want zeta equal to 1, I'm going to be critically damped. I'm going to be here.
Okay.
If I want zeta greater than 0.45, then this is the region I'm allowed to operate in. Together? Again, this comes from the properties of the second order system. This region here represents zeta greater than 0.45. Any poles in this region is going to have a zeta that is greater than 0.45. Good? Again, I did not explain how we found this intersection. For the time being, just trust me. If I have k equal to this value, my poles are going to be at this location. Okay. So we met the first requirement. Now I'm going to come and calculate the steady state error due to ramp. And this error, we're going to calculate the velocity constant, which is going to equal the limit as s goes to 0 of s multiplied by g of s, which is going to equal to 4.188 divided by 1 multiplied by 5, which is going to equal to 0.38. And therefore, the steady state error due to a ramp is going to equal to 1 over kV, which is going to equal to 1 over 0.838, which is going to equal to 1.19. Okay. What was the requirement on the steady state error to a ramp? Less than 1. What did we get? 1.1. Did we meet the requirement? We did not meet the requirement. What can we do to make it 1? Excellent. So to decrease the error, it was suggested that we can increase kV. Make sense? If I increase kV, if kV is 1 or greater, then this is going to be 1. Can I increase kV? Why can't I increase kV? Why can't I increase kV? Here's a star waiting to be labeled.
KV is defined by that intersection point. You can't change that. You can't change KV.
More like, more precisely.
Isn't kV the velocity?
The velocity constant, but I mean, kV, this is the formula for it, S multiplied by G of S. How do I increase kV? What is this 4.188?
You have to change.
This is K, isn't it? So if I want to increase kV, what is the only factor I can control? K, isn't it? If I increase K, I can increase kV. Make sense? But why can't I increase K?
If you increase K, you'd be further along the root locus, right?
And
And then you would not be meeting your other requirement.
excellent,
It would go up.
excellent.
Fail.
Aw, you get a star.
See, never give up. Excellent. So, if I want to increase K, I mean, somebody looking here, say, oh, just increase K, make K 1, it will have the steady state error to around equal to 1. But then I'm going to go back here and say, oh, but if I increase K, what's going to happen? Remember, the root locus starts here and goes this way. If I increase K, I'm going to be going to this region. This region is not allowed. This is the allowed region to work in. So this is my allowed region to meet the overshoot requirement. If I want to meet the overshoot requirement, I have to be operating within this range. If I'm operating at the edge here, and the steady state error is 1.19, if I were to increase the K, it's going to cause me to operate somewhere here. I'm going to be operating here if K is greater than 4.188. And if it is here, then the overshoot is no longer going to be less than 25%. Is that clear, everybody? So how do you meet these requirements? We have to change the dynamics. We have to change the shape of the root locus so we can meet both of these requirements. K alone, changing K alone, we're not going to be able to meet these requirements. Okay, let's do another. Is that clear, Fort Walton? Okay. Let's do another example. So, given the system below, okay. So if I have this system here, and I'm going to plot the root locus for this system. This is -1. This is how the root locus looks like. And T of S is going to equal to K divided by S squared plus S plus K. So if I look at this system, if I'm operating along this branch here, what is the settling time for this branch? If I'm operating here, what is the response going to be? Underdamped. So let's say I'm operating at this point here and this point here. The response is going to be underdamped. What is the settling time? The settling time, if you remember, is equal to 4 divided by zeta omega n. What is zeta omega n equal to? What is zeta omega n? The real part of the pole location is zeta omega n. Together? So going back here, what is the real part of the location going to equal to? 0.5. So this settling time is going to be 4 divided by 0.5, which is going to equal to 8 seconds. Okay. Now, let's say that if I look at this characteristic equation, the characteristic equation is the s squared plus s plus k, and remember this is equal to s squared plus 2 zeta omega n s plus omega n squared. Second order system. So 1 is the 2 zeta omega n, k is equal to omega n squared. Let's say that we are asked the system is required to have omega n that is equal to 4. And let's say that that requirement is coming from the rise time. So if omega n is equal to 4, then what is k? If omega n is equal to 4, what is k going to equal to? Omega n is equal to square root of k, and therefore k is going to equal to 16. Okay. And at the same time, if omega n is equal to 4, then 2 multiplied by zeta multiplied by omega n is going to equal to a 1. From here, to zeta omega n is equal to a 1. And therefore, zeta is equal to 1 over 2 multiplied by omega n. And therefore, zeta is going to equal to 1 over 8. Now this zeta results in a very high overshoot. And therefore, if we have a requirement that we want to reduce the overshoot, we have no control over the overshoot. In order to meet the omega n equal to a 4, we're going to have an overshoot that is very large. Is that clear, everybody? So therefore, if I want a settling time that is 8, I want omega n that is 4, and at the same time I want an overshoot that is modest, that is less than that of a zeta equal 4.8, I have to change the dynamic of this system. I have to change the shape of this root locus. Is that clear? Again, the root locus gives you some flexibility. Looking at this root locus, when I start when k is very small, I'm operating here, over damped, critically damped, And then underdamped, that's about all the responses that you can control. It's underdamped with a settling time that is going to equal to 4 over 0.5. If I increase k, I'm going to get higher overshoot. And that is the flexibility that changing only the gain on the root locus is going to give you. Okay. Now, we're going to be discussing changing the dynamics of the system through the controller design. So what we're going to be doing is we're going to be adding another block to our system. And that block is called the controller. What is this block going to do? This controller is going to be adding poles and zeros to the system. And by adding poles and zeros, we're changing the dynamics of the system, and we're changing how the root locus is going to look like. Make sense, everybody? Okay. What type of controller are we going to be looking at? So let's divide this into 3 parts. We're going to be looking at a controller that will improve the steady state error. To solve the problem of the first example that we've done. So we're going to look at controllers that will improve the steady state error. We're going to be looking at controllers that will improve the transient response. And we're going to look at controller that will improve both. Make sense? So we're going to look improving steady state error, controllers that will improve the transient response, and we're going to look at improving both. Now the controllers that are going to improve the steady state error, we're going to be looking at 2 types of controller. The first one is the PI controller, which is the proportional plus integral. And the second controller is the lag compensator. And the controller that's going to improve the transient response, we're going to be looking at the proportional plot derivative. And we're going to be looking at the lead compensator. And then we're going to look at combining them with the PID controller. Okay. What is the difference between the PI and the lag compensator? This one uses an active circuit. This one uses a passive circuit. What is the difference between the PD and the lead compensator? This one uses an active circuit. This one uses a passive circuit. Together? What is the difference between the passive circuit and active circuit? What else? What is the difference between an active student and a passive student? Oh,
Engaged.
probably does not relate back. Okay, an active circuit. Anybody wanna try? Is a circuit that requires a power source. A passive circuit does not. So if I take a resistor capacitor connected together, I build a circuit. If it does not require a power source for the circuit to work, then it's a passive circuit. Make sense? Active circuit, I need a power source. Who can give me active circuit that you've seen in the lab? What is it? Op amp. Excellent. If I build a circuit with op amp, if there's no power source, the circuit's not going to work. So that is an active circuit. Make sense?
So what's an example of a passive circuit that doesn't need a power source?
Yeah. Passive circuit?
Yeah, what would
Here. This is a passive circuit.
Like what kind of use would that have?
Here. A filter. We're going to see it. We're going to...
When we put in input to it, it doesn't change
The input can be a power source, but the circuit itself does not need a power source.
okay.
Does that make sense? I'm not saying the whole system does not require a power source.
Just a portion of it.
That circuit that we designed, this part, does not. I can connect it to a power source, but the power source is used as input, not to power the circuit. Versus an active circuit where you have an op amp, you still have this input as,
But it has to have a.
but this one has to have a power source.
Okay.
Make sense? Thanks for asking. I mean, good question. Okay, but we will see both of them, and hopefully that will become more clear. So we'll continue on Monday, and we're going to be looking at the controller. And please study the root locus, because we're going to be using it. And this is going to be the bulk of the final material. And the final is worth, I think, 40% or 40%? Okay, so don't say I did not warn you. From previous experiences,